probability distributions, and section 5.1 is specifically on, well, probability distributions. Some basic concepts, though, first about these probability distributions. They specify a specific random variable. It has a single numerical value and is determined by chance for each outcome of a procedure. And each outcome is represented by a lowercase letter like x, and a random variable is denoted by a capital letter, such as capital X. Or it doesn't have to be X, it could be Y, Z, A, B, whatever. A probability distribution gives the probability for each value of the random variable in a table, formula, or graph. A discrete random variable specifically is a collection of values that is finite. Or it can be a continuous one that it does not end, type of thing. A continuous random variable has infinitely many values where the collection of values is not countable. The requirement, though, for a probability distribution is that every probability distribution must satisfy these two. So, the first being that the random variable x is numerical, not categorical, and its number of values are associated with corresponding probabilities. And then the sum of all the probabilities has to be equal to 1, where x assumes all possible values. And each probability must be between 0 and 1 inclusive for each individual value of the random variable. Alright, so for example, let's say let x be the number of goals within 2 births, where x is a random variable because its numerical values depend on chance. With 2 births, the number of goals can be 0, 1, or 2. Does this example satisfy a probability distribution? And well, we can make a table from it, right? If we look at what happens with 2 births, and let me draw a table here to denote this. You can either have a boy or a girl based upon the birth. So I'll draw a boy and a girl in both of these to draw the little table here. So as such, from this you could have 2 boys. You could have a boy and then a girl, or a girl first and then a boy, or 2 girls. Hence where the 0, 1, and 2 come from. So we can make a table of these values and their associated probabilities. So the values of the random variable can be 0, 1, or 2. And how many times does 0 occur in this table? Once out of a total of 4 options. So its probability is 1/4, or 0.25. For one goal to happen, that occurs twice in this table, out of a total of 4 options. So 2/4, or 1/2, has a decimal of 0.5. And likewise, for 2 goals, that happens once, that is also 1/4, or 0.25. So this is the table for that. And we could see from this, x is indeed a random variable. A random variable. Again, because we could have 0, 1, or 2 goals here within those 2 births, and we have this particular table up here, which is always nice. The second one is that if we add up all of these probabilities, so 0.25 plus 0.5 plus 0.25, if we add all that up, we get a value of 1, which is what we want. And for the third one, each probability must be between 0 and 1, right? So if we look at the probabilities in our table, all of those are between 0 and 1 inclusive. So all 3 of these here are satisfied. And as such, it satisfies a probability distribution. Yes, the number of girls in 2 births is a probability distribution. Probability distribution. Based upon what we've seen about probability distributions so far in this section. Our textbook, and assignments using the notation of 0 plus to represent a probability value that is positive, but is also very small, such as 0.00000012. Rounding these values to essentially 0 is misleading since it does have a probability greater than 0, despite it being very small, and we can't call it completely impossible because of that. We can graph a probability distribution as a probability histogram, where the vertical scale shows probabilities as opposed to relative frequencies in the histogram. And another way to express a probability distribution is by considering a formula over the values of the random variable. Let's take this next one. Hiring managers were asked to identify the biggest mistakes that job applicants make during an interview, and the table is based on their responses, based on data from the Adecco survey. Does this describe a probability distribution? Well, 2 big things should jump out at you. Number 1, the variable here is not numerical. X specifically is categorical in this. And a random variable cannot be categorical. Alright? So it fails the very first definition of a probability distribution. But despite that fact, we can also see here, if we add up all these probabilities, we get a value of 1.57. And that is much greater than 1. So because of these 2 things, it is not a probability distribution. For the parameters of a discrete probability distribution specifically, the mean takes the sum of each value of the random variable times its associated probability and adds them all up. The variance, sigma squared, this takes the sum of the squared deviations about the mean, so x minus mu squared, times its associated probability, p of x. We could also write that as the sum of x squared times each associated probability minus the mean squared. The standard deviation is just the square root of that number, of the variance. Typically, results are rounded by carrying 1 more decimal point value than the number of decimal places used for the random variable. Note, there may be special times where more precision may need to be used to correctly reflect the true mean. Expected value is a theoretical mean outcome of a random variable for infinitely many trials. For discrete random variable x, the expected value e of the mean value of the outcomes is the expected value is the mean, which is the sum then of each value of the random variable times its associated probability. So, for example, based on the probability distribution for the number of girls in 2 births, which we got this table for, assuming that boys and girls are equally likely, which they are not, from example 1, we want to find the mean, variance, and standard deviation. So the mean of a random variable x, we're going to take each value of the random variable, multiply it by its probability, and add them all up. So 0 times 0.25 plus 1 times 0.5 plus 2 times 0.25. Toss that into a calculator, you get an answer of 1.0 goal. For the variance, I want to take the sum of each value of the random variable minus the mean squared times the associated probability. Alright, and we could draw ourselves a little table here to help us adjust to that. This is x. Each value of the probability was 0.25, 0.5, and 0.25. If we want to take the value of the random variable minus the mean, 0 minus 1 is, well, negative 1. 1 minus 1 is 0. And 2 minus 1 is 1. Let's say next we want to take the square root. We want to square each one of these. So x minus mu squared. This will make 1, 0, 1. And now for the actual individual calculation for each of these. We take x minus mu squared times the associated probability. So 0.25 times 1 is, well, 0.25. 0.5 times 0 is still 0. And 0.25 times 1, 0.25. When we add up this column, we get an answer of 1. Of 0.5. So the variance will be 0.5. 0.5, and then the unit of measurement for this is goals squared, which is a very weird unit of measurement for this, I know. But regardless, that's what we get. The standard deviation just takes the square root of that number. So square root of 0.5. Touch then to calculate, we get an answer of about 0.7. So 7/10 of a goal for this. And I don't know why I put an S there, because this one is not a more than one amount. So 0.7 of a goal would be the standard deviation. And when it comes to the values of the probability distribution, we can have significant values based on this range rule of thumb. So we call the vast majority of values should lie within 2 standard deviations of the mean. A value is significant if it's less than 2 standard deviations away from the mean. If it's at least 2 standard deviations away from the mean. So significantly low values are mu minus 2 sigma or lower, and significantly high values are mu plus 2 sigma or higher. And not significant values are between those two, so between mu minus 2 sigma and mu plus 2 sigma. So based on example 3, we found that with 2 births, the mean number of goals is 1.0 goal, and the standard deviation is 0.7 of a goal. Using these results, we want to determine the range rule of thumb to determine whether 2 goals is a significantly high number of goals. So because of this being 2, we only need to look at the mean plus 2 sigma, since subtracting them is not going to give us a value of 2 or more. Doing this, we have 1 plus 2 times 0.7. This will make 1 plus 1.4. That's 2.4. 2.4 goals would be the unit of measurement. 2 is less than 2.4. So no. 2 goals is not significantly high. Not significantly high. in this particular example. When it comes to the significant results, the significantly high number of successes is if the probability of X or more successes in N trials is 0.05 or less. So probability of X or more is less than or equal to 0.05. Significantly low number of successes is the same thing. If the probability of X or less successes in N trials is 0.05 or less, probability of X or less is less than or equal to 0.05. If, under a given assumption, the probability of a particular outcome is very small, and the outcome occurs significantly less than or significantly greater than what we expect with that assumption, we conclude that the assumption is probably not correct. And just for one more example of this, assuming that boys and girls are equally likely, find the expected number of girls in 945 births. This, we just take 945 and multiply by a half. This gives us 472.5 girls. This would be the expected number of births. Is expected out of 945 births. Again, this is just saying that if we take a large enough number, studying a large enough number of 945 births, we would expect 472.5 girls as the expected number based upon this. Thank you.